Hi, and thanks for joining us today to hear about our proof of concept for a Lidar-integrated underwater imaging system. I'm Darya Akkaynak, formerly at the Harbor Branch Oceanographic Institute and currently at the University of Haifa.
I'm Walter Britton, the CTO of BEAM-C, based in Florida.
I'm Mike Twardowski, research professor from Harbor Branch Oceanographic Institute at Florida Atlantic University and specialist in ocean optics.
I am Fraser Dalgleish. I'm a senior LiDAR scientist at BEAM-C Associates.
Let's get started. We know that the color of the ocean water gives us great insights regarding the type and concentration of particles in the water. But that the ocean water has color is precisely the reason why the colors of everything else in the ocean are hidden in the photographs we take underwater. Without the degrading effects of water, underwater imagery would have increased visibility, which could mean more accurate navigation or obstacle avoidance for a vehicle, more robust and generalizable AI for detecting, recognizing, counting, tracking objects, and with increased performance in doing so in real time or offline. And overall, it would mean improved science because we could automate more of our marine imaging workflows and reduce the tedious and expensive manual work that goes into analyzing images and videos. So why don't all cameras have built-in algorithms already that image the underwater world without water? Well, there are several scientific and technological bottlenecks, but arguably the most important one is the ability to estimate distance to every object in the scene, and to be able to do so in real time. Because underwater, not only are colors lost as a function of the distance between the observer and the scene, but also an occluding layer of fog grows as a function of the distance between the observer and the scene. Let me demonstrate that with a real-world example. I took a color chart and mounted it on a mooring line at 17 meters depth in the Red Sea. Then I swam to it from about 8 meters all the way up to 30 centimeters while photographing it along the way. The photos you see here are the raw images that my camera captured. You can already see that there's a curtain of fog, also called path radiance, blurring the appearance of the chart when it is further and further away. So you can see better. Now I'm going to computationally remove the path radiance. I can do that because I know the distance to each chart. Now, all charts at all distances are sharper. But we still can't see the colors of each patch on the color chart, because even though we removed the path radiance, there is still distance-dependent light attenuation. So again, using the distance of each chart, I will calculate the relevant parameters to reverse the attenuation so we can recover the color of each patch at every distance. In short, distance is a critically important piece of information for reconstruction of colors and contrast in underwater images. But how do we get distance underwater? Usually with acoustics, but we could also do so using a single off-the-shelf camera and by taking multiple images, or by using multiple cameras. In all these cases, however, we'll have to deal with difficulties with estimating distance accurately to objects far away and estimating distance to moving objects like fish, and we'll also have to deal with high computational costs for real-time applications. There are also specialized sensors, like LiDAR, that capture superior distance and 3D scene structure in underwater environments, even in turbid conditions and even for faraway objects. They're very expensive and bulky, and this has kept them out of reach of marine science thus far. But we believe these disadvantages can be overcome. So, we teamed up with BEAM-C Associates and used their PLLS7500 LiDAR to see how a Lidar-integrated camera would work. The PLLS7500 is a rather compact underwater LiDAR that can have up to 30 meters range in clear conditions. Here's how we designed the proof of concept study. The LiDAR captures a high-quality 3D point cloud, and we obtain two 2D projections from this point cloud, one for range, one for intensity. At the same time, the camera records a frame, Then we register the LiDAR intensity image with the RGB image from the camera and translate that alignment to the range image. This results in an RGBD image, which is sufficient for color reconstruction using state-of-the-art underwater computer vision. In this work, we use see-through for all color reconstruction. At the end of this process, we have each RGB frame color-corrected, which means we also have a color-corrected 3D point cloud. First, we did controlled experiments in the laser testing tank in the TTC facility of Harbor Branch. We simply mounted the LiDAR on a linear drive, mounted a compact Sony camera on a pole which we manually lowered and raised into the water, and fixed an LED strobe next to both. Then we lowered our carefully designed artificial coral reef, decorated with color charts, mounted on a truss, which gave us plenty of structure and depth into the scene. With the camera and the strobe positions fixed and remotely controlling the linear drive, we scanned the coral reef for a total of 72 different imaging scenarios. We varied the imaging distance between the truss and the camera. We varied the available light, and we varied the water turbidity, simulating visibility conditions commonly encountered in coastal and open water imaging surveys. So what did we learn from 72 different experiments? We gauged LiDAR performance by whether or not the checkerboard in the back right corner of the scene was visible. When we imaged the scene from up close, the checkerboard was at 6.9 meters from the camera, and when the LiDAR was at its furthest position, the checkerboard was at 10.4 meters from the camera. And up until the beam attenuation coefficient at 532 nanometers was roughly 0.67, we were able to resolve the checkerboard with the LiDAR. The compact Sony we used, however, reached its limit way sooner at about half of the C-value at roughly 0.31. And in terms of color reconstruction, not surprisingly at all, the best results were in the clearest conditions when imaging was done from the closest distance. Here's the raw image from the clearest water and from the closest distance, and here's the color reconstruction. And here's the limiting case when there wasn't enough signal recorded at the camera to reconstruct the checkerboard, though the LiDAR could resolve it no problem. Encouraged by our results in the test tank, we put the camera in the same housing as the LiDAR, mounted the entire sensor on a Remus 100, and went on a mission to image the wreck of the cargo steamer Copenhagen on the east coast of Florida. The Remus did several passes crisscrossing the wreck, and the BeamC LiDAR recorded a high-quality 3D point cloud of the wreck from which we obtained the range and intensity maps needed for color correction. Then we used see-through, offline, to color correct the imagery captured by the camera frame by frame. The registration and the warping of the intensity image only had to be done once, since the geometry between the camera and the LiDAR did not change. On this deployment, we measured a Secchi disk depth of about 8 to 9 meters, corresponding to about half inverse meters for the beam attenuation coefficient, which is higher than what we found as the limiting case in our tank experiments. There can be two reasons for that. The first is that we actually used a different camera. We used a machine vision camera for sea trials. And the second is that there was a lot more ambient light at the wreck site compared to the indoor and optically well-sealed test tank facility. In the end, we obtained a high-quality color-corrected 3D point cloud and generated a texture map 3D model of the wreck without the degrading effects of water. Where does that leave us? Well, we demonstrated proof of concept for a Lidar-integrated underwater imaging system. We used a LiDAR that is already commercially available and camera sensors that are also off the shelf. We saw with this LiDAR that it can sense about 3 times further than the cameras we tested, so there is room to improve the camera and the optics. We will work on making the relevant algorithms real-time, which is actually straightforward, and design an imaging system that can be easily utilized by divers as well as robotic platforms. This work was entirely funded by Schmidt Marine Technology Partners. Thank you.